Okay, so last time we started talking about what we mean by a stationary sequence, and we will continue from there. So when we say we have a sequence of random vectors, so by stationary, we just mean that for any subsequence with the same length, that is the subsequence, we have xi to xi plus k. And this I could be anywhere in the sequence. And this k must be integer starting from 0. So in this case, we mean that given a fixed k, these subsequences have the same joint distribution. And this k could be any k. So that means this will imply that all the random variables, x1 to x2, and so on, they have the same distribution. Identical distribution is what we what's implied by this stationarity. And also what it says is that x1, x2, x2, x3, and so on. So all the adjacent pairs have the identical distribution. And also you can have adjacent triplets and so on. So that's what we mean by changing this k. And this stationary sequence is a very special type of sequence. And you can see that what we called IID is even more special than this, because here we just say x1, x2 have identical distribution, but they could be correlated. While when we say IID, then it means they're all independent. So you see that IID is a special case of this, and the stationary sequence is more general than IID, but still it's pretty special as it is. So last time we said that if we have this stationarity, a very important consequence is about covariance. So what's implied is that for two random variables in the sequence xi and xj, their covariance only depends on the gap, the absolute difference of I and j. So this depends on their covariance. So that means once I look at the covariance of, say, xi and xj for I and j between 1 and n, but they are not equal to each other, right? So if I look at all of them, then how many pairs would I have? So if I write about all the pairwise covariances for those I and j, I could write I doesn't equal to j, covariance xi and xj. And by symmetry of this covariance, I can write it as 2 times I less than j, covariance xi and xj. So we can do this in general, but because of the stationarity, because of this property, I can rewrite the sum by enumerating all the possible I and j gaps. So we know the gap, because they're not equal, the gap must start with 1 and end with n minus 1. That is when I is 1, j is n. So therefore, I enumerate the gaps, and I call this gap k, which goes from 1 to n minus 1. And for each gap, all the pairs should share the same covariance as x1 and x1 plus k, because this pair has exactly gap k. But how many pairs have the same covariance? I'll do a counting. When k is equal to 1, I can easily see there are n minus 1 pairs. When k is n minus 1, there's only one pair. So the number of pairs with gap k, we can show it's actually n minus k. So that's why we can rewrite the covariance sum in this way. And because we can say that this covariance only depends on the gap, and I can give this a notation. So for this one, I just denote it as gamma of j minus I. This difference as the specific term for this covariance. So in other words, translating it to here, I can write this as just 2 times summation k from 1 to n minus 1, n times n minus k times gamma k. So therefore, I can simplify this summation of covariances simply based on the gamma 1 to gamma n minus 1. Okay, that's what we said last time. So trying to simplify the covariance. And why does it matter? The reason is when we want to look at the variance of the summation, when we want to write out this variance, when there is no independence, then the general formula would be equal to the summation of each xi's variance times that covariance term. This is what we have. And also, due to the stationarity, x1 to x2 to xn, they have identical distribution. So I can write their variance using a common term, sigma squared, the term we like to use. So this will give us n sigma squared. And for the second covariance summation, because of the argument here, because of the stationarity, I can write it as 2 times gap from 1 to n minus 1, n minus k, gamma k. So this is the way we can express the variance of the sum. And you can see that it only depends on these parameters about my random variables. Sigma squared, gamma 1 to gamma n minus 1. So a total of n parameters will specify the variance of the sum. Okay, so that's what we talked about last time. Do we have questions about this? Okay, so today we are going to make this stationary sequence a little bit more special, or adding a one constraint. And we will call this sequence as what we said, called it as m-dependent sequence. Okay, and this m is a given integer. So m is 1 or 2, and so on. So it's fixed, and it's one of the positive integers. So what do we mean by m-dependent sequence? So it says that the two random vectors, x1 to xi, okay, this is my first subvector, and xj to xj, and so on. So it could be xj by itself, or I just go further down to the sequence. I don't care how long it is. Now I want to say that they are independent if j minus I is greater than m. So this is what we mean by m-dependent sequence. It means that in my sequence, if my random variables are apart by at least m, if their gap is at least m, then they're independent. So therefore, it's stronger than this general stationary sequence because we may have dependence for nearby random variables. However, we are, it's more special than the stationary sequence because we have this independence assumption. But it's more general than IID, than the are independent because here we may have dependence nearby. Okay, so I'm just going to show you one example, two examples about the M stationary sequence, which we will see and after we talk about the theoretical result later in the class about the asymptotic distribution of the sum of a M stationary sequence. But I'm going to give you two examples for now. So here, example one. So let's say that we have x1, x2, IID. They are an IID sequence. But if we are interested in this statistic, Sn defined as summation I from 1 to m, xi times xi plus m. So I pick two random variables m apart and multiply them and then take the sum. So in this case, you can see inside my sum, let's say I define, if I want to study the asymptotic distribution of Sn, then I want to write Sn as summation of n random variables, right? And each random variable yi would be xi times xi plus m. Then if we write out the sequence of yi's, we would actually have what? So y1, y2, yn, what would they be? They will actually be x1, x1 plus m, x2, x2 plus m, and here xn, xm plus m, and so on. So the question is, do we have independence in this yi sequence? The answer is no, because you see this term is involving x1 plus m. And somewhere in my sequence, I may have x1 plus m times x1 plus 2m, right? This would be my definition of y1 plus m. So I will encounter a term later in the sequence. They share x1 plus m. So they are dependent. They're not independent. So in this case, if I want to derive the asymptotic distribution of Sn, we don't have the tool yet because all the results we have obtained so far, the IID CLT, central limit theorem, or the Limburg-Feller theorem, they all deal with independent random variable sum. So we don't have the tool yet. But you see that this sequence of yi's is actually an M-dependent sequence. The reason is that, yes, this term and this term is dependent. But after this term, when I start with x2 plus m, x2 plus 2m, so you can see that everything after this term will no longer be dependent of this one. So they will all be independent of this one because of the IID of the xi sequence. So therefore, this sequence is an M-dependent sequence. Does it make sense? Okay, this is example one. And example two is our familiar coin tossing example. So let's say that we have x1, x2. They are IID from the Bernoulli P tossing. So they follow the same success probability. And the statistic I'm interested in, or the random variable I'm interested in, is the number of consecutive ones. So what does that mean? So in this sequence, if I have 1, 0, 1, 1, 0, 1, 1, 1. So here the Sn will be equal to 3 because this are considered as 3 consecutive ones. So by this definition, you see, to capture this number, how can we write it in terms of my x1 to xm? So clearly for the first one, right, I want to know whether this is wrong. So we can count it by counting the starts of the consecutive ones. So how do I define a start? For the first one, if it's 1, it is a start. So definitely x1 should be here. If x1 is 1, we get a start of a consecutive one. And how about the following? For the following to be qualified to be a start, I need this position to be a 1 and the previous one to be a 0, right? That's how we can define a start. So therefore, starting from 2, when I start from 2 and to n, so my total sequence is length n, I would actually do this multiplication xi times 1 minus xi minus 1. So this is 1 only when xi itself is 1 and xi minus 1 is 0. Only when both happens, I get a 1. So therefore, you see what I have here by writing this out, you can see that I'm having this interesting summation. So if I don't look at x1, but just starting with I equals 2, you can see the summation is having this interesting yi. I would define it as xi times 1 minus xi minus 1. And therefore, Sn will be equal to x1 plus summation of yi for 2 to n. So then you can see that I need to be able to quantify this summation if I need to describe the asymptotic behavior of Sn. And then what's yi? Yi would involve 2 consecutive random variables in my sequence, right? Xi and xi minus 1. So to be exact, if I write it out, y2, y3, then y2 would be x2 times 1 minus x1. x3 would be x3 times 1 minus x2. So clearly, they are not independent because they share the same x2. But you can see after this, right, I will have x4 times 1 minus x3. So after this one, all the remaining yi's would be independent of y2. So therefore, you see, once the gap is greater than 1, I have independence. So therefore, this is what we call one dependent sequence. In other words, in our m dependent sequence, m equals 1. So in those 2 examples, you can see that when we want to describe the asymptotic behavior distribution of some sum of not independent random variables, then this m-dependent sequence formulation would be useful. Okay, so coming back to what we want to say with the m-dependent sequence. So you see, with m-dependent sequence, what's implied here? Back to our covariance. Here, covariance xi, xj, right? It's the m-dependent sequence if we also have the stationarity. So we say m-dependent stationary sequence. What do we have? So once the gap j minus I is greater than m, then this gamma will be 0. So in other words, adding this to here, we know that this can be simplified as we just need sigma square gamma 1 to gamma m. And we don't need anything else because they will be 0. So you see, the number of parameters we need to describe this variance is reduced to m plus 1. And m is just the dependence structure. Okay, does it make sense to us? Okay, great. So remember what we have here, right? So let me just try to erase this part and let's see. So with M dependent stationary sequence, this summation variance of the sum can be simplified as, and so K just go from 1 to N, M because we have M dependent sequence, M minus K, gamma K. Okay, so we have that. Now we will have our important theoretical result for about the asymptotic distribution. Okay, so let me write it here. Okay, so this is what we call the theorem. So you can think about this as the version of the central limit theorem for the sum of stationary M dependent sequence. So let's say that we have x1, x2, and so on. They are a stationary M dependent sequence of random variables, and we just use our general notation to denote that they have the same mean, mu, and the same variance, sigma square, which is finite. And they have the covariance xi plus k denoted by gamma k, okay? And this gamma k is 0 if k is greater than m. And this is implied by the M dependence. Okay, so then the result we want to give you as the asymptotic distribution is that, again, the formula we're familiar with, root n times xm bar minus mu. This is the average of x1 to xm minus mu. We convert in law to a normal distribution with mean 0, and the variance is equal to sigma square, the variance, times 2 times k from 1 to m gamma k. Okay, so we have this familiar normal distribution, but the average is actually having a bigger variance than under the IID case. Under the IID case, the central limit theorem tells us that the asymptotic variance is only sigma square, but this is sigma square plus an additional term. Or I wouldn't say bigger because it depends on the signs of gamma k, because we know that the covariance could actually be negative, right? It could be positive, it could be negative, but we're just saying that these covariances would influence the distribution of this xm bar. Okay. So, any questions? Right, and also I can give you an extreme counter example for you to think. So suppose that I have this x1, x2, and so on, all identical to each other. So in this case, I basically just have one random variable. I'm just repeating it. So in this case, is it satisfying our M dependent sequence requirement? Any idea? Yeah. Right, there's no finite M. The M must be finite. So in that case, no matter how large M is, right, you still have dependence after the M. So it clearly violates the M dependent sequence, right? And then in that case, what's xm bar? It's just that random variable itself, right? Because it's repeating. So I take the average, I still get that one. So clearly I wouldn't have asymptotic normality, no matter how large the n is, because the distribution of xn bar would always be the distribution of xi. And xi may not be normal. So therefore xn bar will not be normal. So in this case, you can see why this M dependence assumption is very important. So even though we may not have the perfect IID case, but still we need to have the independence to be the majority of my sequence, while dependence is only restricted to a subsequence of a fixed length M. So therefore, compared to the dependent part, the independence is dominant. And we will see this plays a bigger role in our proof for this theorem. So therefore, you see, with that extreme counterexample, you can realize the importance of this, or the necessity of this M-dependent assumption. Okay. So how do we prove this? This will be the majority of today's lecture. So we will try to prove this theorem. And I found this theorem very interesting personally because it reflects a way to think about how do we deal with this random variable sequence. Okay, so the idea is that we want to simplify things to start with. And so first of all, without loss of generality, we assume mu is 0. So we don't need to worry about mu, because if it's not 0, we can always do xi subtracting mu, xi minus mu to make it centered. Okay, and the second thing we want to do is that we want to work with the sum, because it's easier to work with the sum in this case than the average, because the sum divided by n is just the average. So working with the sum is enough. So we define Sn to be the summation of xi. And we want to make use of the M dependence to help us. So I'm going to use illustration here to help you understand the idea behind this proof. This is not in the notes, it's just a mathematical description, but I think the illustration here will help our understanding. So what we want to do is that we hope to create some partial sums. So let's say this is 1 to m. What I want to do is that I want to take 1 to k as my partial sum. And I know that this part is the thing I want to work with. Okay, and how do I utilize the M dependence? I want to create subsequences far away with distance m away so that they are independent. Okay, so the idea is that I'm going to have a subsequence k here, and then I'm going to move m apart. Okay, and I get a subsequence k again, and then move m apart, and I get a subsequence k again. Okay, and then move m apart. And whatever is left over, I call this remainder R. So in other words, I'm dividing my whole sequence length m by a number of k plus m segments. So I have km, km, km until I don't have anything. So let's say that I have s segments, each with length k plus m, plus some remainder r. So by this definition, I know that the length of r must be less than k plus m, right? By the definition of a remainder. So what's the benefit of doing this? The reason is that what I want to do is that in order to obtain this asymptotic normality, we always start with our most basic one, central limit theorem, to help us to obtain the asymptotic normality. So I know that if I take the partial sum here, so let me call this based on the notation, I call this VK0, okay, because it's segment 0, and this is VK1, segment 1, and VK2. So I start with 0 to be consistent with my notes. So 0, 1, 2, maybe so on. But what I want to say is that this is the partial sum of this segment, of this segment, of this segment. And because they are apart by length m, they are independent. So I have VK0, VK1, VK2 until VKS minus 1, the last segment. VKS minus 1. These things are independent. Actually, IID. And IID because they are summation of the same number of random variables, right? And the random variables are stationary, so they have the same distribution. So they are IID. And then what I can do is that I will be able to use central limit theorem for these as long as I let my S go to infinity, which I can. Because if I fix K, and M is also fixed, right? M is fixed by the M stationary, by the M dependent sequence. Once I fix K, then N goes to infinity, implies S goes to infinity. The number of segments go to infinity. So therefore, central limit theorem could be applied to this part, to the summation of this part. So, and I will define this as SNK prime. And this is just the summation of the VK0 to VKS minus 1. So in other words, I would call it J from 0 to S minus 1, VKJ. Okay, so I will use central limit theorem to handle this part because of the IID. And what's remaining? You see, clearly my SNK prime written in here is only one part of it. I still need to deal with those M segments, right? These things, and finally the remainder. I need to handle 3 parts. So for these, I will call this WK0, WK1, WK2. Okay, so following the notation here, I will define SNK double prime as summation J from 0 to S minus 1, WKJ. So the summation of those M segments will be the second term I need to handle. Okay. And finally, but here I want to let you know that the CLT doesn't apply here. Okay, we cannot use it. The reason is that they are only apart by K, not M, not necessarily M. So this is something we cannot do, but we will think about how to deal with that later. And the last term is the remainder. Here, I just give this partial sum a notation R and K. Okay. So the idea is that if we want to derive the asymptotic distribution of Sn, CLT can help us with this part. And our goal is to let this part, the normality of this part, to dominate our result. So in order to achieve that, what we want to do is that we want to let K go to infinity. So you see, because the K is a fixed K we set ourselves, we can adjust its length. If we make it really long, then the proportion of the M segments will be negligible. So we'll be dominated by the segments of k. And again, this thought is from the fact that we have n goes to infinity. And if we let k go to infinity, then we can make the proportion of m compared to k negligible. So therefore, this term will be what decides the distribution of this term. So that's the rough idea. And in order to show that, we would actually give you a very interesting lemma as the theoretical foundation to complete this proof. So one thing you need to think about here is tricky is that on the left-hand side, we only have one n, and we want to let this n go to infinity. We know that. On the right-hand side, we need to deal with this k, which is something we created. And we want to let this k go to infinity along with n go to infinity. So how can we connect the asymptotic distribution of a term on this side to the asymptotic distribution of this side? Okay, so let's first talk about the lemma before we revisit this proof. So in the lemma, we are going to use a different set of notation. So we denote Tm as the sum of z and k plus x and k. And we have n 1, 2, k 1, 2. They're both integers that can go to infinity. So we have three conditions. The first condition is that this second term, x and k, needs to converge in probability to 0 in n, uniformly in n. I need to say this. N as k goes to infinity. So what does that mean? And this is based on the definition of convergence in probability. And now we have two indices. One is n, one is k. And we want to, as k goes to infinity, we want the convergence to be uniform in n. What does that mean? It means that, so given any epsilon greater than 0, so we should be able to find k. There exists a big k such that the probability that the absolute value x and k larger than, sorry, I should say this, given any epsilon greater than 0, and I need to have this any delta as well, sorry about that. So I have any epsilon greater than 0, delta greater than 0, then the probability that the absolute value of x and k greater than delta must be less than epsilon for any n and any for all k, and for any n and any k greater than this big K. So in other words, this holds for all n, no matter how large or small n is, but as long as k is greater than this existent k, I would have the x and k absolute value very small. So that's what we mean by this uniform in n, convergence in probability to 0 as k goes to infinity. Okay, this is the first condition. And the second condition is that once we, so basically it means that this term is very small, negligible. And then how about this term? We have the z and k converge in law to zk as n goes to infinity for each k. So this is different. We are not saying uniformly uniform in k, but we're saying for each k, once we fix k, but we let n go to infinity, we will have this sequence Z1K, Z2K, Z3K, this sequence will converge in law to some ZK. Okay, and so basically here we fix K, but only change N. And the third condition is that when we have ZK converge in law to some Z as K goes to infinity. Now we are changing K. So with those three conditions all together, then we are able to have this interesting result we want, that is Tn converge in law to Z as n goes to infinity. So this is a lemma because it lays the foundation for the proof we need here. You see, what we need here is the asymptotic distribution, what Sn converge in law 2 as n goes to infinity. But we involve k here on the right-hand side. And we need to deal with k goes to infinity along with n goes to infinity. So therefore, this lemma provides the same setup here. So in other words, you can think of what we have here is this xn as nk prime, right? We said that when we fix k but change n, central limit theorem applies. So you will tell us the limit to something that depends on k but not n, right? Let n go to infinity. But finally, the k needs to go to infinity, just as in our condition 3 over there. Now we need let k go to infinity and find the limit, right? And that will be the limit we want this Sn to converge to. So you see, the connection between that lemma and the result we want to get here is simply because we have two layers of convergence or two levels of asymptotics. One is about n, one is about k. Okay. So I think I will not try to give you too much details about the proof of that lemma. That the proof is pretty detailed enough in the notes, but I will try to give you some quick essence about how we proved it. Okay, so basically the key idea is to, when we try to show the convergence in law here, we're still using the definition of convergence in law. That is the convergence of the CDF function. Okay, so let's say that we find the point Z, which is in the continuity set of the CDF of the limit, right? For such continuity point, we will need this probability that Tn less or equal than Z converge to the probability that Z is less or equal than Z by the definition of convergence in law. That's what we need. And then how do we express this probability left-hand side? Use the definition is equal to the probability Z n k plus x n k less or equal than Z. That's what we have. And then how can we decompose this so we are left with some CDF of Z and K only? Because that will let us use condition 2 and then condition 3. And then we need to separate Z and K and X and K. But one thing we can use is condition 1. That is, we know X and K is going to be very, very small. So using that idea, again, because of this definition for probability, convergence and probability, again, we're going to use the trick we have seen before. That is, we are going to divide this into two joint events, Z and K plus X and K less equal than Z. First, when X and K is less or equal than delta plus the probability z and k plus x and k less or equal than z, given that x and k is greater than delta. Just dividing it into two events. Okay, and then we know what we want to do. So the first event is that, you see, these two things would imply an event, right? So this plus this is less or equal than delta, but this itself has absolute value. So this is, sorry, not z. Z is here. And we know that this is z and k plus x and k is somewhere here. But x and k itself has absolute value less than delta. So no, so we know that z and k cannot be greater than z plus delta right here, right? Even if x and k is negative delta, when that happens, then z and k can be at most z plus delta. So in other words, this event implies z and k is less or equal than z plus delta, right? Because this event implies that event, this event is bigger. So we have less or equal than for the first probability. And the second probability clearly is less than the probability with just x and k greater than delta. So you see, with this inequality, this less than that, this thing can be connected to the CDF of z and k. And this probability alone is going to be controlled because of this convergence in probability to 0 of x and k. So this is small, negligible, and this we're going to use condition 2 to show that, oh yeah, this will converge to the probability of zk less or equal than z plus delta. And finally, you see n will be away, n will go away. And finally, we let k go to infinity and apply condition 3. And we will be done. So I'm just trying to make it here. So to summarize what I said, this is going to be small. And this, the first term, delta, we would use the condition 2 to show that as n goes to infinity, fixing k, this will converge to zk less or equal than z plus delta. Okay, but of course, z plus delta must be a continuity point of the CDF of zk, so that condition 2 can apply. But this is a technicality, and we have some discussion in our proof in the notes to say that because you pick this zk to be a continuity point of fz, so you may pick some delta. You may pick some delta so that you can have z plus delta as well as z minus delta to be some continuity point of that zk as well as z. So it's mathematically, this is something we can prove. Okay, condition 2 will lead us here. And finally, condition 3. Let k go to infinity. We will go to, okay. So therefore, you see, for the upper bound part, we can relate this probability zn less or equal than z to this probability z less or equal than z plus delta. So in other words, this is the CDF of ztn at z. This is the CDF of z at z plus delta. So we have this delta to worry about, but we can also choose delta to be sufficiently small so that the difference between this and the difference of, because z is a continuity point, so when delta is sufficiently small, this and this can be very close, just some small difference, and that can go down to 0. So you see, for the upper bound, we can prove this part. And for the lower bound, we can similarly show that So in other words, we can similarly show that still by this type of inequality, okay? But for the lower bound, you see, I need to switch things a little bit. So right here is that I have, just let me clarify. So right here is I have probability, just rewrite things, z and k plus x and k less or equal than z, right? What I have here is this is less or equal than probability z and k less or equal than z plus delta plus probability x and k greater than delta. Okay, so I have this side. And now what I want to do is that I would like to change it to this. So by symmetry, you will see what I want to what I have. So if now I have this as prop z and k plus delta less or equal than z, okay? Then by symmetry, what would I have down here? It's less or equal than the probability of z, let me see, z and k greater than z and k less or equal than, right, so then z and k less or equal than this. Okay, sorry, my bad. This is what I want to say. So if I have this, the second line is z and k less or equal than z minus delta. Sorry. Right, I think what I want to say is correct. Z and k plus delta less or equal than z. So I'm replacing x and k by delta. So on the second line, then I would have this probability of z and k less or equal than probability x and k greater than delta. Sorry, let me think. Okay, so I'm going to switch those two. Okay, x and k plus delta. That's what I want to say. X and k minus delta. Yeah. So okay, so z, okay, x, z and k less or equal than z minus x and k. That's what I want to say. So I switched x and k and delta in those two ways, in those two things. So this will give me a lower bound on the probability of Tm, which is z and k plus x and k less equal than z. So this is z and k plus x and k less or equal than z. So for this, now I'm obtaining a lower bound, and the lower bound is greater or equal than the probability z and k is less or equal than z minus delta minus the probability x and k greater than delta. Okay, so with this lower bound and the same argument I will apply. So this term is small because of the convergence in probability of z and k down to 0. And this term, I'm going to first, by condition 2, go to the probability of zk and then the probability of z. So to put the lower bound over there. So in other words, by those two ends, I'm going to show that, so the probability of zn less or equal than z, sorry, tn less or equal than z is going to converge to the probability of z less or equal than z. So for this part where I was confused myself is basically when I make this upper bound. So previously I start with x and k, and now I just by symmetry, I replace x and k by delta. So I will have something similar. Okay, so this is the lemma. So basically the key is to have what we want is here. So in other words, coming back to what we have in our theorem here, we will need the right-hand side to have an asymptotic distribution for the term that doesn't go down to 0 in probability. For that dominant term, we need to find its asymptotic distribution as k goes to infinity, or n goes to infinity first, and then k goes to infinity next. And that limit will be the limit in probability for our Sn. Okay, so we're going to use the lemma for now to derive what's the asymptotic distribution of Sn. Okay, so that's x and 2. Okay, so with this lemma, we are going to mimic its notation for our terms here. And you know what we want, you see, because we subtract the mean to be 0, right? So we now here with mean being 0, root n times xn bar is our target. And we are going to define it as our Tn in the lemma. And then because of the relation between xn bar and Sn, this is actually equal to Sn divided by root n. That's our Tn. Okay, how about these two terms? Because we write Sn as 3 terms, Snk prime, first term, Snk double prime, second term, Rnk, third term. So after this separation, we are going to define what's in our lemma, what's z and k and what's x and k. So x and k is something we want to deal with most easily. And the most obvious choice is just this r and k part divided by root n. The reason is that you see this part is constrained by the length r, the remainder. And we know that this remainder must be shorter than k plus m. So once we fix k, m, fix those two things, right? When we let n goes to infinity, we know that the segment number s is going to infinity, but this remainder will stay as fixed. So that's why if it's not changing with n, so we can easily let it go down to 0. So we just define z and k, the major part, to be Snk prime plus Snk double prime root n, and that 0 part, x and k, to be r and k divided by root n. That's our setting. Okay, sorry, I think I'm bad. My bad. Sorry. No. This is I mixed the two terms. I will put r and k here. Sorry, and I'll put s and k this here. This doesn't change with m. Okay, actually, it doesn't matter whether I put r and k here or there, because this term is negligible anyway. So the most important part is this s n k prime divided by n. That's the dominant term. And this is the term s n k double prime. It's about this m segments, and they are restricted by m. So different from these things because the k can be large, but this m is fixed. So this is the term I really want to go away. But this r and k, the remainder, this one is the most negligible one. So in the notes, we put it here, but actually if you put it there, it's still okay. Okay, so with this setup, now let's try to check the lemma. How does we have the lemma condition satisfied? Okay, so first, this s and k. Again, by its definition, it's the summation of SIID. Okay, so s and k prime alone is the sum of SIID. Okay, how about its first term, VK0? Its first term, VK0 is its first term. Is actually equal to x1 added to xk, right? By its definition, it's partial sum. So we have expectation of VK0 equal to 0. And the variance of this partial sum, VK0, is equal to k is what? Is actually equal to what we have in the formula. So that's actually something we need to deal with, right? And also, if you think about this VK0 is the partial sum of 1 to k. So it's basically sk. You see, it's basically what we have sk. So this is something we can write out using the formula we derived, but we'll just keep it as just a term, okay? We call this variance sk. Put it here. So therefore, for this sk prime itself, by central limit theorem, as s goes to infinity, what we have over here is this partial sum because it's mean 0. The sum divided by its number of IID, that's s, root s. This would converge in law to normal distribution with mean 0, and the variance would be the variance of a single term, and that's the variance of sk. Okay, this is what we have from central limit theorem. Okay, and how do we relate this to root n, right? Root n is what we need, but we are having root s here. What's the relationship between s and n? That's this relationship. So you see, when we divide n to this side, right? So what is square root of s divided by n? Clearly, we can see that it's convergent to, as n goes to infinity, k fixed. Okay, so for every k as n go to infinity, this is convergent to 1 over k plus m by definition. Hence, together, s n k prime divided by root m, that's what we have, can be written as this constant s times n root, s divided by n root, times s n k prime divided by root s, okay? Convergent in law. You see the limit, this limit will enter the variance after being squared. So I would actually have the limit as normal 0, variance sk divided by k plus m. Okay, That's what we have for this part. Okay, how about this part? This R and K divided by N. Maybe I can erase this part and keep the statement. How about R and K divided by root N? Okay, we know that for this part its variance can be easily written out because it's just for the remainder R terms. Because of stationarity, you can think of R and K just as summation of x1 to xr. Okay, and we actually have this thing, if you recall. And so first of all, this n would come out, right, after squaring. And the variance of the sum. So we, based on the previous derivation, we have is the R times the variance, right? And then the covariances. How many covariances do we have? So for every pair that doesn't, so we have basically 2 times R choose 2, right? So essentially we would have the R times R minus 1 covariances to deal with. R minus times R minus 1 pairs bidirectional. But we know, this is something I want everybody to know. For the covariance, its absolute value is always less or equal than the variance. And we know that. The reason is because if you think about what do we mean by the correlation is the covariance divided by the variance. So therefore, if you remember that, then you know the covariance is actually smaller or equal than the absolute value of covariance is smaller or equal than the variance. So therefore, we can safely say that this variance is less or equal than by all the covariance terms replaced by R squared. Okay, so even though we do this bold inequality by enlarging all the covariances to the variance, still, you see this term is only as big as R squared sigma squared divided by M. Because the R is fixed, right now K is fixed, so R is fixed and N goes to infinity. As N goes to infinity, the variance is going down to 0. We know that. So that's why I said this term is easiest because it's negligible. And where does the variance go down to 0? And this thing has mean 0. We know that. So by Chebyshev's inequality, we can easily show that R and K divided by root N is convergent to 0 in probability. We have this for any K, and so I won't say this is for fixed K and any K, each K, maybe I should say each K, and N goes to infinity. Okay, so we have this part. And now what else? So essentially, this part is dealt with by this convergence into 0 in probability. And we are all fixing K for now, okay? So only talking about K, N going to infinity. And for the second X and K part, how do we deal with this? And okay, so for this condition 1, that's about this X and K. So coming back to here, so let me just restate what we have already. So this is a result we need. This is the first result we obtain. This is the second key result we have, okay? So what we are left is this last part, this last piece, x and k. Okay, for the last piece, how do we do? So the variance, again, we look at that. Variance of x and k, we want to show it will go down to 0 in probability. Variance of x and k can be written as, so it's the, again, it's as pieces, okay? So I erased that part, but you remember, still as pieces, and each piece has length m. So therefore, right here, let me write that down. So x and k double prime is sum of s pieces. And so the first piece, we call that wk0. So that one is actually equal to, you see, xk plus 1 multiply addition to xk plus m, the segment of length m. And we know that this has the same distribution, equal distribution as Sm because of stationarity. So in other words, it's summation of S pieces, and each piece has the same distribution as Sm. Okay, and how do we deal with this summation then? So I said that when we just fix k, right, we cannot assume the S pieces to be independent because the k may be smaller than m, so the m dependence will not apply. But now if we set fix k to be larger than m, then those pieces would become independent. Then in this case, we can calculate this variance of S and K prime more easily. So now we have independent S pieces. So now for this sum of independent pieces, this variance will be equal to S, the number of pieces, times the variance of each piece. That's Sm. Okay, we have that. And finally, you see, for variance of S and K, by its definition, is the S and K double prime divided by root n over there. And therefore, is now S times variance Sm divided by n. Okay. How about the relationship between n and s? Recall that we have n times s times k plus m, right? Plus r. That's what we have. So once we have s divided by n, and also we have here this result. When we have k fixed, n go to infinity, then s divided by n will converge to 1 over k plus m. So we know that this is actually less or equal than variance of Sm just divided by k. So you see, for this term, once we have this inequality, something interesting happens. That is, in the upper limit, or in the upper bound, sorry, in the upper bound, we don't have n anymore. Only k stays there. And the reason is because of this cancellation of s and n. S goes up as n goes up. With this cancellation, we only have k left. And with k left, it makes things much easier for us, right? Now look at condition 1. What does it say? K will go to infinity, uniforming n, but now n is gone, so we don't need to worry about n. And when we let k go to infinity, clearly we would have, and m is fixed. Don't forget this, m is fixed. When we let k go to infinity, then this variance x and k will go down to 0. So that will give us condition 1, because with the variance go down to 0, again, we would have x and k converge in probability to 0 as k goes to infinity for all m, uniform in n. So we achieve that. So therefore, condition 1 is satisfied. And that's the thing we need, the third key result we need. Okay, so with 1 and 2 and 3. So finally, what we want to say is that this Tn, or right here, right? So when we have its limit, we would actually, its asymptotic distribution would depend on the asymptotic distribution of this term. And now we have this converge in law to this thing, So n is already going to infinity. So here, when s goes to infinity, it's equivalent to n goes to infinity. But we're not done yet. The reason is that we still need to let k go to infinity in the limit, so that finally the limit of Tn doesn't depend on k, right? But how do we deal with that limit? What happens to this when k goes to infinity? That's the last step we need to address. Okay, so to fill in the final piece, let's take a look at that. Variance of sk, the first k length segment divided by k plus m. Okay, so, and k will go to infinity. So recall that what we have here, right? So in the beginning of the class, we derived this variance. It's k times sigma squared plus 2 times, okay, so now I'm not going to use k, I'll just use j from 1 to m gamma j. So the covariance of gap j, and divided by k plus m. Okay, so what happens here? Sorry, I missed something. No, k minus j. This is the key, gamma j, yeah. Okay, when I let k go to infinity, I will get some easy cancellation, right? When k goes to infinity, k and k plus m becomes equal. K minus j divided by k plus m has a limit 1. So basically, as k goes to infinity, I will have sigma squared plus 2 times j from 1 to m gamma j. And that's it. So therefore, you see, I obtain my final result. That's exactly the asymptotic variance I have in my theorem. So this proof relies a lot on the construction of that k-length segment. So as I said in the beginning for the illustration, we want to create IID so we can use central limit theorem. So therefore, by creating those k-length segments that are separated by m length in the middle, so we created that IID by utilizing this m dependence property. And with that, we first let k fix so we can use CLT. And finally, we let k go to infinity so we can have those sequence, this part, we can have this part occupy the sum we're interested in. So therefore, we achieve that asymptotic result. So I think this proof itself is very interesting. And also the result is super clean because the final asymptotic variance only depends on sigma squared, the variance of each random variable, and the covariances of gap up to m. Okay, so we are actually running long today, sorry about that. And we will try to come back next time, we will just use this result, try to do the 2 examples we mentioned in the beginning to see if we can derive their asymptotic distribution. Okay, so I'll see you next Monday. And if you need an office hour, you can schedule it with me. Okay, Thank you.